Go.
Okay, so the size of a black hole when you make one, two objects falling together, depends on how much mass you're left with. And so, like Jocelyn is saying, so these are sort of city mass sized things that we're imagining, but with masses of stars. And so if two of them collided, then roughly the size would double. Not exactly, because you lose some amount of the energy to these waves of gravity that are going off into the universe that we'll detect.
Okay.
But mostly about that. So figure about sort of city size scale is what we're talking about.
Also, it's like almost like you're saying like they were like the size of like the Empire State Building, and they were crushed, and they have the same density, and now they're like the size of like a small pebble.
Yeah.
Well,
I don't know.
You need a whole Earth to get to a golf ball. So
Wow.
So just the Empire State Building would have to be pretty small to be a black hole.
yeah.
That's right. And
So
yeah, they're called, scientists call them compact objects because we like to understate everything. They're really, really compact.
we're very serious about this compactness.
Yes.
From the ancient times, the term adamant or adamantine has been referred to as a near indestructible substance, akin to diamond, gemstones, or some kind of exotic alloy. Science fiction has unobtainium. Describe the nature of the crust of neutron stars and how it compares to the fictional variety.
Well, so one of the things that's happening in the crust of a neutron star, or anywhere in the neutron star, is that you have this matter where the gravitational pull is so strong that it's compressing it to super high density. And the thing that happens at these very high densities is that, so for example, for regular matter, say the nuclei, there's a lowest energy for the nuclei that are around our day-to-day lives, which is iron. So that's why you can gain energy by fusing nuclei together up to iron, or you can have things that are heavier than iron. The nuclei can radiate energy and go down to about iron. So there's this ground state kind of configuration for the matter. So this happens on the entire crust is something like the nucleus of iron. Well, that's not true. In the interior of the neutron star, you have something like the nucleus of iron. Everything is compressed together, and it's lost all its energy out, radiating heat and neutrinos, and it's in the ground state of material. So it's very uniform, and it's very compressed, and it gets in the center. It's actually a pure liquid. And then on the outer layer, you have heavy nuclei that form a very strong lattice.
So it's like boron carbide. It's really dense.
It would be kind of like the density of iron on the outer layers before you're in the atmosphere and stuff. But it's a little weird because it's got lots of neutrons. It's under such high pressure that it's got a different elemental form, and then the nuclei are locked together in a very rigid material.
So that would make for like wonder materials. Like it would be like a great body armor.
Oh.
Well, the thing is.
Well, I was just going to say, but it's so massive for being so small. How heavy would body armor made of neutron stars?
Yes, there's a couple problems.
Yes.
So first off, if you try and take a bit of this material away from the neutron star, it doesn't like to stay that compressed. It will try and return to its sort of normal, regular configuration of stable atoms alone isolated. So it will expand dramatically inside and basically explode. And then the other thing is this.
Which means bye-bye for you.
Yeah, and then there's a beautiful evocative thing that I don't remember, but 1 teaspoon of this matter is some billions of kilograms in weight on Earth.
Well, they're almost the size of black holes. So if the Earth mass black hole is like this, then I don't know, maybe like, a few times twice that. So we're talking about, something this size of a small ball being the mass of the Earth, then making enough of it to where, even if you could keep it compressed,
you'd be walking around with like several Earths around you.
This wouldn't be good for your health.
No, you'd have some problems there.
Yeah, so fairly impractical for that.
What kind of plate tectonics can be observed or deduced with current mathematical models and observational technology in a neutron star's surface crust?
Well, so we've seen, so we look at, we observe neutron stars a lot of the time because they have a very strong magnetic field coming out from their poles, and this tends to send out radio signals. And the neutron stars are spinning, so their poles kind of sweep around, and you get this blip of radio pulses every time the neutron star goes past. And there's because of magnetic interactions, this slows down, but sometimes what you'll see is a dramatic change in the rate of slowdown. So this is called a glitch. And there's an idea that this is some interaction between the crust and the fluid underneath that can explain this. But I think all these models have the crust staying as a uniform solid crust. If you try and do models of the material that's in this crust, you find that it tends to it tends to kind of settle down to a very perfect lattice structure fairly quickly. So even if there's some defects in it, it stays very strong, and so it's still just a solid uniform crust around the star that sort of settles into the comfortable configuration. So we haven't seen any like continents moving or anything like that. We've just seen the whole shell as a whole shift in how fast it's spinning.
Well, what happens to the crust of a neutron star when it collides with another star, suggesting it doesn't turn into a singularity? Where does it go?
Oh, well, okay, so if you have two neutron stars merging together, this is actually a subject of current research, and some people argue that the crust will actually break when the two stars are quite far apart, and some people argue that actually the crust will melt, and some people that the stars will actually just sort of crash together with their crusts intact. But as soon as they crash together, that basically melts the crust. And by melting, this becomes a fluid, and then the stars kind of merge together into a fluid blob, and they can send out kind of tidal tails of material to go around them. But most of the dynamics of this is really driven by the core dense matter inside the stars, so the crust has a hard time influencing. It can't really resist the two stars crashing together.
So to Professor Lovelace, what kind of quantized space-time effects can be observed within the star system of a neutron star?
Okay, so I guess I should say I'm not so much of an expert as Jocelyn about neutron stars, and I'm also not much of an expert about quantum effects. The reason is, the things that I tend to study more are black holes, and when black holes are the sizes that we've been talking about, the effects of quantum mechanics turn out not to matter very much. Quantum effects matter on very small size scales, so you might imagine having very small black holes where it might matter, but for black holes the size of the sun or so, they don't tend to be so important. Maybe you have something you want to add. I was going to just say. Well, go ahead.
Yeah. So I mean, when you determine how big a neutron star is going to be, that's determining how much this matter is going to resist being squished in.
Yes.
And that you need a quantum theory to fully describe what happens to the particles as they're compressed. So you need to understand quantum mechanics and particle interactions to understand how big the neutron star is going to be. But it's not sort of something you see directly. You just see how the matter responds and how the fluid behaves as the two stars merge together, and that can tell you something about these quantum effects. But it's not a direct thing you see in the wave.
Okay.